Hey, this is Will from SRT Amplification, and I haven't done a video in a long time, so this is going to be a first in a while. Actually, I shot some footage here a while back on some things, but never got around to duplicating it. So today we're going to be looking at a device. Tony from X-Ray Tony B, I'll put a link to his channel down in the description, did a video just a couple of days ago, maybe last week, about a transistor curve tracer that he had built himself. And it basically gave the IB curves for a transistor, right? So at various base currents and how it's linear through, you know, a wide range of voltages and everything like transistors are. But that got me to thinking about a little device that I have. If I can find it here. Oh, here it is. And I'm going to do a little video on this. It's the Hameg. I believe it's I don't know what the model number is. Hameg Instruments. Oh, the HZ-65. It's the HZ-65 component tester. And it's basically what a lot of people refer to as an octopus or a curve tracer or a component tester, or you know, there was another brand that was big that did these called Huntron, that actually had a video, a screen that actually showed you. But this is something that you can actually hook to your oscope, so you don't have to, you know, that Huntron tracker was kind of all in one kind of thing, or Huntron tracer or whatever it was called. And I'm just going to show you guys how to use this, and it's a pretty neat little device. You can build one of these on your own. This one's a lot more sophisticated than it has to be, because it's got all of your transistor sockets and switches between each pins. It only tests between 2 points at a time, so you can only do, you know, you can do 3 pin devices or 3 contact devices, but you can only do between, you know, 2 of them. Resistors, capacitors, anything like that. You can stick them in this, or you can clip them on. Got some banana clip or banana jacks here. And then it's got a minimum current, medium current, max current, and that's just basically changing the voltage that you're going to be putting on it, on your device under test. So you use this with the oscope, and I'm going to show you how to use this. But before I plug this into the oscope and show you how to use it, I wanted to kind of go over a little bit of theory on how this thing works. Let me get my camera set up here. All right, so I'm just going to make this like really simple. This thing, well, there's my pen's going all, it's kind of cold out here, so you have a transformer here. So this thing's got a transformer in it, right? Okay. If you want to build, there's all kinds of instructions on how to build these things online. All you need is like a little filament transformer. So, you know, 6.2 volts or 6.3 volts or whatever on this side, on the secondary side is plenty. That's all you need for most of these. This one's a little more complicated. It's got some, you know, switching mechanisms and everything. But really and truly, this is what you kind of have here. So let me zoom in here. There you go. So you got your transformer here, okay? And what you want to do with this component tester is you kind of want to get a idea of what is happening in a device, right? So when I show you, when I put this on there, you'll see a little bit better. But basically, if it's an open circuit, you're going to have all of your voltage dropped across that open circuit and therefore no current. So you're going to get horizontal line on your oscope, right? So your x-axis is your voltage on the oscope. You're going to be running this thing in XY mode. So, and then your y-axis is going to be your current. So if you have a short, so you put your device under, you short out the lines here. You don't have any device under test. You just short these lines out. You're going to get a vertical line, meaning there's current flowing through it, but there's no voltage dropped across it because it's a short, right? So those are your two extremes. You know, a horizontal line and a vertical line, and then a resistor is going to be somewhere in between, right? And then a capacitor is going to be some kind of, because you have a phase shift. This is a linear device. This is not a linear device. So you have some kind of oval or circular looking shape there. And then, you know, for diodes, you may have, you know, at a certain voltage, the current's going to start going up. That's your knee voltage right there. With the Zener diode, you know, it may go negative and then have a Zener breakdown voltage here. So anyway, basically how it works in the circuit is you have a resistor that you're basically putting a voltage across. You're making a voltage divider between a resistor and your X probe, right? Your X probe. And then this is going to have a ground connection right there. And yeah, right. And then this will be your Y probe, basically. Right? So basically how this is working is your X probe is going to be your device under test here, and that's going to be a voltage divider with this resistor, whatever this resistor is. This is simple. Like there's more components in there than this. There's various other resistors and stuff, like I said, to get the different current levels and all that. And then there's some switching in there for the leads and everything like that. But anyway, at the simplest form, this is what you have, really. And so when you take a voltage across this resistor right here, it's basically kind of directly proportional to the current. So your Y probe is really showing you the current, okay? Basically, the reason being is, like I was talking about earlier, if you short this one out, right? Max currents is through the device under test, right? So the voltage drop that your oscope is reading between ground and here is a directly proportional to whatever the current is flowing through here, because all the current is flowing through this device at that point, right? So that's how this works. Now, unless this is a, you know, a 1 or a 10 or whatever, you can't really correlate it to the actual value. I mean, you could go in there and actually find out what this value is and then find out what the voltage is across this thing and correlate it. But that's not what we're really wanting to look at. We're just wanting to look at current through there. So then if I have this open, so if I open this up, take this out of here, all my voltage is going to be dropped across the device under test. So I won't have any current, I won't have any voltage across this, so that there's no, it's going to look like an open. So I'm going to basically get a horizontal line. I'm going to have the full voltage across this port right here, right? Because that's open. So that's kind of how it works. I know this is kind of simplistic, but really what you're looking at is you're kind of looking at a current via a voltage drop, right? Which is what oscopes look at. Oscopes can't see current, right? So you're basically looking at a current through a device via a voltage drop across a resistor, and then the x-axis you're looking at voltage. So you get all these various different shapes. So that's what we're going to look at today. So let's, enough of that stuff, right? I probably butchered that all up. I know you guys are going to tell me about it in the comments, how wrong I was about this. That's fine. I'm not good at explaining things very well. But anyway, let's look at it on the oscope, and you may see a little bit better. I'm going to be using my Tektronix 465 here, so I'm gonna go ahead and get it warmed up because it takes a while to warm up. A lot of people don't realize that you can use X. Oh, this thing warmed up really quick. Look at that, man. Beautiful trace. A lot of people don't realize that. Adjust my intensity here so maybe it doesn't blind you guys. A lot of people don't realize that you can use XY mode on these old analog scopes. I actually prefer analog scope myself. But if you have a digital one like this, you know, your Rigels or Tektronix or whatever you got, there's a menu in there to go into XY mode. With this, you just take the time domain all the way to the far counterclockwise, and you're in the XY mode. You can see the dot stopped right there. It's no longer sweeping in the XY mode. So anyway, I can change this thing here, position here. All right, so it's right there in the middle, right? So let me get this thing set up. This has to be plugged in. To a 120 outlet. I'm just going to plug it in here to my Variac, I guess, for the now. And then you'll want to get your probes, right? Now you can use BNCs to BNC on this. This has got a BNC. This has got BNC connectors on it, right? So you can just go in BNC, BNC. So let me find my BNC connectors here. BNC, BNC, BNC. Where are they at? Where are they at? Got so many cables. It is crazy. There's one set. So you want your Y mode, or your current, and right here on the thing it even says Y current, right? X voltage, which really they're both voltages, but okay. Anyway, you want your Y current on channel 2. So we'll put that on channel 2. Hey, I'm doing this on the fly, man. I didn't rehearse this. All right, so I don't want to get all kinds of comments. But I didn't rehearse it, so hey, whatever. We'll put this one on channel 1. This is going to be your X axis, or your voltage. All right. And then I've got some little clippy things here that I usually use for this old Fluke multimeter. I'll just stick those right in here, and we'll use those for our components. We may stick a transistor in the transistor tester too, but I just wanted to show you guys a few. Probably look at a capacitor and a resistor, but so I got the banana jacks in there, little clippies. So let's just get let's look at this first. Okay, so let's get this thing kind of calibrated here, because I'm not seeing a line on here. So I got these things. I got to power this thing up. So let's power this thing up. Here we go. Sorry. Okay, we're powering her up here. All right, so what's going on here? Okay. I don't have these on the same division, do I? You want to make sure that your divisions are on the same division. So there's 5, 2. There we go. Okay. And you want to alt these, right? It's going to go back and forth between channel 1 and channel 2 really fast. So put it on alt. See, if you put it on just 1, you're just getting 1. If you put it on just 2, you're just getting 2. Maybe you can do 2. Yeah, I guess you can put it on channel 2 and it'll work. I I did have it on invert. I don't know why I had it on invert. That's weird. Anyway, let me position this. Okay. So yeah, you can have it on channel 2, and it'll do it for you. Oh, okay. I had that on. Ah, see, I had my channel 1 on AC couples, so I don't know what the deal was. Okay, so yeah, I haven't done this in a while, fellas. So there we go. I remember. I remember what's going on now. Okay, so the way I have this hooked up, I got both of them on DC. Um, I don't know why my thing jumping around here. I got them both on DC coupled, input coupled. I don't have it on invert, and I have them on the same volts per division, and I have this set up on my vertical mode into uh, channel 2, and it even says right here, use channel 2 for XY mode. Okay, so you can't use it in channel 1, right? It's not going to give you what you need. You can, I think you can use it in alt mode because it'll go between them really fast. But channel 2 is really the one you wanted to have it on in XY mode. It even says right here on the little thing. So you know, it's not going to get you confused, right? I probably confused you more than you'll get confused. But anyway, it's weird how the video. So let me see. That is weird. The video, you're actually seeing the trace move. Huh. That's weird. So with the refresh rate of the video and everything, the camera's capturing that trace moving. To my eye, I see a solid line. It's not moving at all. Anyway, let's see here. Um, put this in. We're not triggering on anything, so that don't matter. Anyway, so I'm going to show you what this looks like when you short it out. Remember I said it's all voltage, no current right now, right? All voltage, right? Between here and here, all the voltage is being dropped across here. No current because I don't have a complete circuit, right? If I go no voltage, in other words, short these out, so there's no voltage potential between these two leads, and I short these out, then I should have no voltage and all current. So I should be looking for a vertical line, right? So let's see. And there it goes, vertical line, boom, right? So right there, that kind of tests your setup. So we're looking good. So let me grab a resistor here and see. Well, you know what? Let me grab a diode. Well, I've got a little bridge rectifier here, so that's not exactly a diode, but it does go through two diodes, or it will go through two diodes if I. Let's try that. So let's put the. See this right here. I probably got this backwards. I'm sure I do. What's going on here? Oh, maybe I had it inverted earlier. That's what it is. Okay, so this shows you a diode right here, right? Again, you guys are seeing this kind of cattywampus. Sorry about the angle there. But at a certain point, which is about 0.7 volts, 0.6 volts or something across one of these diodes, I may be going across two diodes here. You get your current. So at a certain voltage level, past zero, it starts to actually conduct. So that tells you got a good diode. I don't know if I have a Zener diode here or not. Let me look through my bag of goodies here. So I got a whole bunch of diodes. So one of the things that you can do is if you know you have a diode, right? Most diodes look kind of the same. They're either black or they're these glass type, right? And I believe this one is actually a Zener diode. And you can just clip onto these things, and it'll give you indication kind of what it is. So there you go, right there. Perfect example. I know that's a Zener diode. Now I have no idea. I can approximate. I can say, okay, if that's point 0.7, then maybe that's, if half a line there is point 0.7, then maybe two whole lines is, uh, or one line is a half, maybe three, 4, 5. Maybe this is a 5 volt zener or something like that. I don't know, right? But at least you know it's a zener, and that may be a 5 volt zener. I don't know. You could do some more checking to see. Let's see what this one is. This one goes off the screen here. Okay, so this one doesn't have. This one just has a forward voltage drop. Nothing there. Let's see what this one has. Probably just has a forward voltage drop as well. Yeah, forward voltage drop. Now, on some transistors, you'll see a zener kind of a curve on the base to emitter. Let me see if I can show you what I'm talking about. So this should be an NPN. I think it's an NPN if my drawer is labeled correctly. So I'll put my positive lead here in the middle. Let me bend these out a little bit. Now this is where that little transistor tester thing would work better than what I'm doing here. So I'm going to put my positive lead on the middle here. It's an NPN. That's the base. Okay. And then I should have you see that? I have this is a PNP. It's a PNP. I don't know what this label is. Transistor small. I just got this. I got all my other transistors up there, so I didn't actually label this one what it is, but oh, there we go. Okay, so this is a PNP. So I got my negative on the middle, or I may be invert. I don't know what's going on here. Okay, so I'm off the screen here. Nothing. So that's base to collector. Let's see here. Okay, so this one, the base wasn't in the middle on this one. And you sometimes run into that. And that's how you can kind of, you can see, okay, see from this one right here, I have, see, that tells me I'm collector to emitter to collector. I have no current flow through there whatsoever, so no voltage drop, or all the voltage is dropped across the transistor at that point. So I'd have to look at the pinout on this one. I just pulled this one out. But let's look at an LED. That's kind of cool because LEDs have lower voltage drops or higher voltage drops than a normal, rectifier diode or something like that. Whoa, that's all kinds of weird. Did that thing actually light? Oh, you know what? I probably need to put min current on that. This thing's got a current limiter on it, so you don't have to worry about putting a. You don't have to worry about putting a. See, you can move this thing over here. So really, where this is breaking is really of no relevance unless you. But anyway, if we line this thing up the way we had it before, this is breaking over, about 2 times or 3 times more than that regular diode did. I think red diodes have like a 1.8 or a 2 volt drop, something like that. So, yeah. And then if we try another color, let's say this, I think I got an infrared one here and a green one. We'll try a green one. We'll try the green one first. See what it's got. What am I doing? Here we go. It's a little bit higher, not much. It's right around the same as the red was. Let's try this infrared one. These little clippies are not working real well. Okay, here we go. And see, it's a little bit less. It's a little more than that regular diode was, but it's quite a bit less than the red and the green one. And then I have a yellow one here. Let's try the yellow one. It's about the same as the red and the. I don't have any blue or any other color, so that's it. I think the blue ones are significantly higher. Yeah. Here's a resistor. So you remember I told you that open is horizontal line, shorted we had the vertical line, right? And had the vertical line, and a resistor is going to be a diagonal line, or should be. Now, it's not. The reason it's not because this is a high value, and I probably need to turn up the current here, and it's not. What? What value is this? Get on my spectacles here. It is a 225. So it is 2.2 megs. Wow, 2.2 megs. So I may not be able to test. See, 2.2 megs of this thing is too hot. It looks like an open. Let's find something a little smaller. Okay, here we go. This is a 370. Oh, 3.7. Oh, so that one's, look at that. You can barely see, but it's not quite vertical, right? That's vertical, and this is not quite vertical. It's just a little off of vertical. It's a very low resistor. Let me find something in the middle. Those are just two that I had laying in there. I got a whole bin of them over here. Find something. Oh, let's see what I got here. There we go. See? And this is what, 444. Well, this is still pretty high, but you can see it's not as high as that 2.2 meg, right? And it's almost horizontal. Now let's put two of these in parallel. That's going to half this resistance, right? Clip these two together, put two of these in parallel, and then it gets a little less vertical or a little less horizontal, right? So varying degrees between really low resistance and really high resistance is going to be, and if you had some kind of calibrated scale here, you could probably determine what the resistance values were. I mean, it would have to be a really fine scale between 0 and 90 degrees, but that's really the deflection that you're going to have there. And it's all based off of that resistor that's inside here that's basically in series with this when you put it in the test. So that's a resistor. Let's look at a capacitor real quick, and then we will make like a bread truck and haul buns. Let's see here. Capacitor. All right. So if you had a perfect capacitor, I believe you would get a perfect circle, right? But because capacitors have resistance and inductance and everything in them as well, you're going to get some kind of ellipse or oval. So this is a zero point 0.1 microfarad film capacitor. And you see here you got some kind of oval, right? Kind of funky. Let's see if it changes here. Kind of funky. Let's see if we need some more current. Oh, there we go. Hey. So it's looking for min current. Yeah, it's kind of a funky circle. See what else I got here. Let's pull out another one. This is a 0.01 microfarad. There we go. Basically, what's happening with an inductor or a capacitor, you're going to get a voltage shift, a phase shift between your voltage and your current. So that's what you're seeing there on the screen. Basically, is that shift. That's kind of what you're doing here. There's a phase shift between the voltage and the current, and because this thing's only looking at voltage and voltage, because there's a phase shift between voltage and current, that it's making itself known in this as well, so you can kind of see that. But that's what a capacitor should look like. If you see something that looks like that, and you're measuring a capacitor, right? Oh, why is my thing not very bright anymore? There we go. If you're measuring something that looks like that, and it's supposed to be a capacitor, then you got a bad capacitor, a shorted capacitor. If it goes like that, then you got an open capacitor, right? So that kind of gives you an idea of what's going on with the component. Now, does it really tell you much more than that? Not really. It's just kind of a handy device. I very seldom use it, but it is, it is there. The only time I've ever used this thing in a practical application is if I had a component that I did not know what it was. That's where it comes in really handy, because then you can at least know what type of component you're dealing with, and then you can do some further tests, right? So if you don't know what the component is, I think this thing's great. It will tell you if you got a short or an open. So gross faults, yeah. It's not going to tell you whether you have any drift in a resistor, or the ESR of the capacitor, or any of that other information that you may need if you're troubleshooting something. But for letting you know, hey, I got this kind of component. I've got, they all, if I put a transistor in here, yeah, it looks like from base to emitter, it looks like it should. From emitter to collector, it looks like it should. From base to collector, it looks like it should. Probably everything's good with that, that component. There still may be something wrong with it. I mean, it may not have the gain that you want in the component, or there may be something wrong with it still. May not be the right component, number one, and so you can't use this to like match things like transistors and say, oh, this transistor's characteristics look like the one I pulled out of it, so I can stick that one in there. No, you can't do that, because it's going to have different current ratings, different temperature coefficients, and the speed, the slew rate, and all that's going to be different. Okay, or it could be different. So you don't know any of that with this tester. But that's what it is. It's the Hameg component tester HZ-65. Like I said, I'll put a link to Tony's video in the description, and you can go check that out. He does a real good job of explaining that little transistor tester, and I believe he's got the if you go to his Patreon page, which there should be a link to his Patreon page on his YouTube channel. If you go to his Patreon page, I think he's got all of that schematics and everything on how to build that transistor tester that he has in there. But if you want to build one of these, they're really easy to build. You can grab a breadboard like this and just make your own. They're really easy, just a few components. It doesn't have to be this fancy. You don't have to have all this fancy switching and stuff like that. Just a little filament transformer, a couple of resistors. Yeah, filament transformer and a couple of resistors really is all you need in this thing. It's that simple. And you can make it a little more fancier if you'd like, but there's all kinds of designs for these. The first time I ever saw a design for one of these, believe it or not, was in I spent 27 years in the Army, 20 years active duty and 7 years National Guard prior to going active duty. But the first time I saw one of these schematics for one of these was in a Navy electronics manual. And I had seen devices like this before, but in the Navy electronics manual, it actually said, hey, build your own. Here, this is your parts list. This is what you need. Here's a schematic. You know, you don't need a Huntron tracker or a device specific. Here, just build your own. Of course, those Huntron trackers are nice. They got the built-in screen. You don't need a separate O-scope for it. They do a lot more and everything, but if you just want a simple component tester like this, you can just build it, and you can even find these online fairly cheap. So if you want something that's self-contained, that's got good BNC connectors and banana clips and that's made really, really well. This thing's it's built like a tank, and it's got a linear it's a real linear transformer in this linear power supply. So it's not, there's no, this is heavy. This is not no switch mode power supply, which you don't need it. You don't need anything like that. You just need a filament transformer. It puts out like 6.3 volts on the secondary and a couple other components in here, and you're good to go. But anyway, I just wanted to show you guys my Hameg HZ-65. I hope you enjoyed the video. Please like and subscribe, and we'll see you in the next one.